data given the model is integral over the parameters of the normal likelihood times by the prior on the parameters. Okay? So this is the central mechanism that Bayesians use to do other kinds of inferences. And if you remember, we went on to an example, this one here, fitting continuous data. So I'm going to try and attempt to actually run a demo. I don't know if it's going to work, but so the idea is that in this particular demo here, it was quite easy. We were thinking about that a single scalar output is a sort of linear combination of these periodic functions, these cosine functions. Okay. So the idea about that is, it's, many things in the natural world are periodic. Oscillations, vibrations, they're all kind of periodic. So particularly in time series, we are very interested in decomposing a signal into its periodic components. So one way to write this more generally is to say, well, W is some linear combination of some function of the input x, and we had this kind of thing, and then we said, well, maybe the output, that's the clean output, and maybe the real output is generated by this clean output, plus some Gaussian noise. Okay, and then the idea was, could we figure out what the posterior distribution is on the weights? If we put a Gaussian prior on the weights W, we'll get a posterior distribution on the weights, and will also be Gaussian in this case. And then we could also integrate over the parameters as well. So just to remind you, because we need to revisit this some of this technical stuff a little bit. So let me just let me just say that one thing that maybe I didn't stress enough is that. So I'm interested in what is the posterior of the way it's given the data, or say just a general Gaussian distribution. So in the sense that this is going to be proportional to the prior times by the probability of the data given the weights. Okay. So in this particular case, we're going to put a Gaussian prior on this, and we're going to put a normal distribution on these weights with, say, some mean 0 and some covariance sigma. And for the data, we're going to assume that this term here is a product of independent terms, the probability of each data point generated from the model. And this itself is a normal distribution in Yn, which has got a mean W transpose Xn. And I think I called the variance sigma squared. So this whole thing then is going to be, when you write this all out, what is that? That's going to be W transposed sigma f minus 1 W half from here. And then from here you get a product over n of e to the minus 1n minus W transpose xn squared over 2 sigma squared. So we recognize we can rewrite this as simply then from here, okay. Then from here, this product you can put in the exponent to give a sum. So we get 1 over sigma squared, the sum over n Yn minus W transposed xn squared. So what we did last time, or one thing you can do, is you can say, well, this is clearly a quadratic function in the exponent. So that tells you that the posterior distribution for W is a Gaussian, because that's what a Gaussian is, it's a quadratic form in the exponent. So we can just simply write that as something of the form, say, e minus a half, say W transposed A, W plus 2 W transpose B. if there's a constant here, that gets absorbed into this proportionality term. Okay, so we're only interested in the W dependence of this distribution. So clearly, the matrix A is given by sigma to the -1 plus the outer product terms of the fixes, okay, scaled by sigma squared. Let me know if I'm going too fast. I don't know if you're familiar with these algebraic notation, just manipulations, but is it too fast or too slow? Is that obvious? It's obvious. Cool. All right, so that's A, and then B, vector B, will be similarly given by, well, it's the linear contribution. Okay, so we want, just the linear contribution in this exponent. This, okay, so what is the linear term? Well, we've got, when you square this out here, you get a linear term, right? So you're going to get something like this minus and this minus cancel. You're going to get 2, so that 2 cancels. So you're going to have 1 over sigma squared, the sum over n of yn xn. So we can identify, we can just write down this matrix and this vector. So if I give you, say, now you know that the distribution is of this form, so I claim that that's a Gaussian distribution. Okay. And why is that? Well, in general, a Gaussian distribution, say with some mean W and some covariance matrix, let's call it sigma again. So the form e to the W minus mu transpose sigma to the -1, W minus mu to -1 over half, and the sum proportionality term. So in other words, this is equal to or proportional to e to the -half W transpose sigma to the -1 W, the quadratic term, and the linear term is just going to give minus, the 2 will cancel, so we're going to have W transposed sigma to the -1 mu plus some constant which is absorbed in this normalization term, proportionality term. Okay, so what this means is, well, this is exactly the same as this, in which A is playing the role of sigma to -1, right? And B is playing the role of this term here. So in other words, then, if you have a distribution of that form, you know that that's a Gaussian with covariance is equal to, the inverse covariance is equal to A, so the covariance is equal to A to the -1. And B is equal to this, so the mean is equal to sigma times by B. So the mean is equal to sigma times by B, where sigma is A to the -1. So the mean is given by that. Okay, so this is kind of nice, right? So, what we've done is we've got these matrices A and B as a function of our data, our inputs and our outputs, and various things like that. And we've realized now the posterior distribution is a Gaussian with this mean and this max matrix. So that's good. And we can do things with that. We can calculate also the corresponding integral. We did that last time actually over the parameters. But what I forgot to maybe explain last time. So if we integrate with the parameters, we can get the model likelihood, which is given by that expression. But actually, there's an alternative, sort of simpler expression, but I'm not going to derive that here. It's actually easier in some sense to derive, but okay. So this example where we had a noisy signal, which is kind of, looks like it's periodic to some extent, and I wanted to clean this up. And it turns out that if you run this Bayesian model selection, you find out that the most likely model is the one which contains 5 cosine components, okay, up to period 5. And so that's that. And then we can basically use this component, this model with 5 components, to clean up the data. Now, how am I going to do that? Well, I'm going to look at the model, the posterior distribution for the model with 5 components, and I'll calculate, in particular, the mean of this posterior distribution. Okay, for that 5 component model, and that will give me the mean parameter vector W, posterior. Okay, so what I can do then is I can say, well, then the mean, if I go back to here, so if Y0, the clean signal is given by W transposed 5x, then the average clean signal is given by the average W transposed times by 5x. So the expected reconstructed signal is given by the expected W transposed times by phi. Okay. So what I can do is I can then plug in my Gaussian posterior mean, and then I can reconstruct my expected clean signal. And that's what I did here. So this is the cleaned, whatever it is, the red is the mean construction. So the dots are, the true, these are the true clean function. I happen to know that because I generated the data from some known model. So you see, it works quite well. It's a very simple problem, but it kind of works. So let's attempt to do something slightly more interesting. We're going to try to do some kind of sound reconstruction now, some waveform stuff. So let's see if this works. I hope the speakers are going to work. Let's see. That's not very loud, is it? Let's see if I can find a way to increase the volume. Did you hear anything? Is it coming through the speakers? Or? These kind of signals look like. Let's plot the true signal. Say this is the kind of, this is what, these kind of sound, this is just a wave file actually. So these are the, I've just taken one of the two channels, the stereo channels here. So these are the very first, half a second or something. There are 48,000 point samples per second. Okay. So it's quite a lot of time points. And if you zoom in, kind of a typical, just a small region, it's still pretty messy, but we can zoom in even more. And you see kind of locally periodic style things, things are oscillating. That's the whole kind of physics of waves and strings are going backwards and forwards, generating these pressure waves. And this is just a pressure difference that we're plotting here. Okay, so what I'm going to do is I'm going to corrupt this signal in some very simple way. I'm going to simply randomly select something like 20% of the values. I'm just going to set them to 0. So as if somehow maybe you were trying to send this signal to somebody over a channel, and maybe you just lost the signal. So we'll just set it to 0, and then what I want to try to do later is to try to reconstruct the signal under this 0 loss. Okay. And we'll explain a little bit more how it's going to work. So the first thing we're going to do is we're going to play the corrupted signal. Okay, so this is a little bit long again, but bear with it, and it may not sound quite so nice. Let's see. Maybe typical kind of noise corruption that you would get in reality, but it's kind of sounds a little bit like those old crackly records you have. Okay, so let's just see what that looks like. Zoom in a similar region as before. Okay, so you can see the zeroing going on here, just random. So I could have plotted the the waveform again, but it's the same idea. Okay, so how can we reconstruct this to get rid of these zeros? Well, there are many things you could do, and I'm going to do a very simple thing. And I don't claim, by the way, this is a particularly good idea. I just wanted to show you a kind of implementation or example application of the simple things we've been doing so far. In fact, there are really much better ways to do this, but they're a little bit beyond the scope of this course. But you can try to do something like the following thing. You could say, well, let's go back to this example here. So we're going to now, let's say we choose a window of the signal. Okay, so I don't know how long it could be. It could be, say, of length, say, whatever, and 50 time steps or something like that. And you saw that the signal is kind of generally locally periodic. So the idea is we'd like to represent this signal within this window as a periodic function. So we could say y of t within this window is, say, some linear combination of, say, wk times by cosine of some So this omega here is just the sampling, the frequency of the signal. Okay, it's just a constant. We need to choose that in order to make sure that we get the right sort of frequency of oscillation. So I can choose a sort of fundamental frequency omega, of the order of, so it would be 48,000 samples per second and beyond that. And then k will be multiples of that fundamental frequency omega. Okay, so it's exactly the same as before. So we will then try to decompose our signal into a combination, a linear combination of these kinds of signals, and the 3-period, the 4-period, etc., up to some chosen period. And I'll just, I'm not going to do the full Bayesian model selection thing. I'm just going to simply fix the number of components. I'm going to just decide that a priori. Okay, I'll choose something like 100, I think. I can't remember the exact number. Okay, so we'll have 100 of these, and we'll try to then represent the signal that we have as a linear combination of these 100 signals. Okay, so that's one way to look at it. If you prefer, another way to think about these kinds of things, and also Fourier analysis in general, is to think of it as a coordinate representation or rotation, right? So we've got some signal. We're going to have this noisy signal, which is going to be like that. It's going to be, in that case, a 50-dimensional vector in Euclidean space. Okay. So what we're going to try to do is to, the way to represent that vector. So in general, you'd have a point, 50-dimensional point here. That's going to be our vector y, which is, it's a vector, it's got the 50 time points vector. So this is going to be the component in the 1, the y1, the y2, and the y3. And that will be our Euclidean representation of the vector in that coordinate system. And all that we're doing actually in the Fourier thing of this cosine decomposition is it's just going to rotate the coordinate system. It's actually an orthogonal transformation. So this is okay. So we're going to use another coordinate system in which I rotate the axes by some amount. Okay, they're going to be another coordinate system, which I'm going to struggle to draw, but you get the idea. So I'll just sort of rotate it in some way, and that rotation corresponds to the particular fundamental frequency that I choose. And then I'll re-represent that vector in that rotated coordinate system. And that's all that Fourier analysis is doing. That's the whole picture. All right, so I'll do that. Right, so I can say, I'll go back to my model here, and I'll say, well, what are the weights? I'm also going to assume I know the output variance. Okay. It's going to be very, very small in this case, because I don't actually really corrupt this signal at all, really, except I delete points. And then what I'm going to do is going to say, well, okay, what is the probability of the data in this case? Well, I'm going to simply take the product over all those points here where I have observations. Where I don't have an observation, where it's 0, the signal, I'll simply not have this term there. Okay, because I don't observe any signal at that point. So what that will mean is that I'll get when I come to do my expression before, where I had the A was the sum over all these data points here. Within the window, I'll have the sum of the time points where I observe the signal only. Where there's no signal, I will not have this term. And similarly for B as well. So when I've done that, I will get a posterior distribution for W, as before. And then I can use that W to reconstruct the signal. Because I have a mean W, so I have a mean W. I'll use that mean W to reconstruct the signal at all time points. So T is here. Is that kind of clear? Clearish? Okay, so let's let me show you that working. Then what I'll do, then I'll do that, and then I'll simply move this window one time point in the future, and I'll repeat the whole thing. So I'll reconstruct, say, the signal at, say, some point in the middle. Given this window, I'll reconstruct the signal at some point in the middle for that W, using that mean W, because there's a signal there, that point. And then I'll shift this window forward one step at a time. I don't like that procedure, but at this level of the sophistication, we'll stick with it. So I'll try to play now the reconstructed signal. It's not perfect, actually. You can hear a little bit. Parameters a little bit better, it would have been pretty much perfect. I mean, I think you ought to be able to solve this problem very, very well. Actually, it's quite an easy problem. Just to maybe show you what the kind of the signal looks like. So let's plot them. So this is the corrupted signal. Let's plot let's put the true signal. And let's put the reconstruction. So just to remind you again, so the red is the reconstruction, the green is the true uncorrupted signal, and the blue is the actual corrupted signal. Okay, so it's not bad, it's not great, but it's okay. So you can see. So, for example, so these points here, right? So you can see that the reconstruction here is pretty good, right? The red and green are almost on top of each other, even though there were 4 points there which are completely missing. Similarly here, this has got 4 points missing, and this has got the signal. Good. So there'll be some points probably that don't work so well because this procedure is a little bit too basic, and I think that I didn't get the parameters really well tuned. But, yeah, so you see, it works kind of. So yeah, you can do all kinds of fun things with this stuff. You can really, if you do more sophisticated things, you really can get very sophisticated, very nice, recovering. So like the noisy recording. So people do pretty impressive things with these kinds of techniques. Actually, it's much more, a little bit more advanced than what you can do with, say, classical, engineering style approaches, where based on filter banks and all this kind of stuff. It's a little bit more sophisticated. Okay, so you can do a lot. My basic point is you can do a lot with what you know already. Okay, so this model is easy because it's a Gaussian, right? And everything is analytically tractable. We can do integrals easily. But in general, this is not going to be the case. So we're going to have to do some kind of numerical approximation to get these integrals or these posterior means or whatever we want to do. So in general, this is our formula. We've got to take this integral over the parameter space. In general, we know we're going to have, if this integral is one-dimensional, then that's okay. If we couldn't compute this analytically, what could we do? We could kind of discretize the interval, and we could then just replace this integral by summation. Right? That would be one thing to do. Just whatever they call that, Simpson's rule, or whatever that's called at school, right? But if you were to try to do that in n dimensions, how many points are we going to need, roughly speaking, in n dimensions? So if I said, I want to have the k discrete points per dimension in order to discretize this integral, how many points am I going to need roughly in say, n dimensions for an n-dimensional integral? So what I'm trying to say is that if you've got some integral, which is, you don't know, is some function of x, and you want to compute the integral of this function, and you don't have it's not one of the known analytic classes. How do you compute that? Well, one thing to do is say, well, just bin up the range, and I'll evaluate the integral, so the function at these points. And then I'll say, well, I just basically approximate then this one, the sum of these, this thing. That's the simple way to approximate that integral. If you were to have, say, 2 dimensions, you can do a similar thing where you now grid up the x1, x2 space, and you've got some, surface now, and you can evaluate the function at each of these points on this grid, and you get this kind of like column sort of volume that you can then sum up over the grid. So here, if I had, say, k bins in x1, I'm going to have k squared bins for 2 dimensions. Now, how's that going to scale in n dimensions? It's going to go k to the n, right? So this is hopeless. There's no way you can do this. So even for a simple, say, apparently simple 10-dimensional integral. If you've got, say, 100 points here, 100 to the power 10 is that's pretty big, right? I mean, forget about it. There's no way you can do that. So, this is a big branch of mathematics or applied mathematics to numerical analysis, to try to understand the best way of approximating these integrals. It's not easy to do. Of course, you immediately can jump on the point, maybe you don't really need all that sort of finesse or kind of refined grid, because the function is not changing that rapidly. So maybe you can kind of get away with using some kind of smaller number of grid points, but maybe you need to adapt it. You need to try to understand where are the sort of the points of smoothness of this function, and you can do something there to approximate it. Okay, so that's a whole new sort of lecture series, but we are going to now attempt to do something even simpler than that. So this is the world's most basic approximation for calculating integrals. Okay, it's even simpler in some sense than this. So the point is that this approximation will scale up to n dimensions. It's not going to be a problem to implement it, typically. It's not necessarily going to be any good, but it's doable. Okay, so we look at this thing here. Let's call this thing some function, say e to the minus f of theta, theta of the parameters. Okay, so why can I do that? Well, I can do that because these terms are positive, right? So I can always write that as e to the minus f. So this thing here, whatever it is, f can be positive or negative, but this thing then here will be positive. So in other words, I define f is the negative log of this expression here. Now, I'm going to have to go back to school, unfortunately, at this point. So I wrote the answer down, but I didn't write the derivation here. So, you remember the Taylor expansion, hopefully. So what does the Taylor expansion say? It says that, let's get this right, so f of x at some point x is approximately equal to, say, f of x plus delta, the first derivative of x, f evaluated x, delta bit over 2, the second derivative evaluated at x, right? Plus something which is cubic in the length, the absolute value of this delta parameter. Okay. So what I'm going to do is I'm going to say, well, let's look at let's apply this Taylor expansion to the function f. And the first thing I need to do is I need to actually write down the vector form of this. So in multivariate calculus, we'd have this scalar becomes this is the gradient vector. So this has got components df of x. That's the ith component of this gradient. And this matrix here, hij, it's got elements d2f by dxi dxj. Okay, so this is the Hessian. And this is the gradient. Okay, that's our classical Taylor expansion. So we're going to use this Taylor expansion to approximate this function f of theta. So let's say that we've got some function f, and let's say that theta star here is the point which maximizes the function. Okay, it's the optimum point here. I'm going to try to approximate this function around this point. So I'm going to carry out the Taylor expansion at theta star, the optimum point, the point where f has its maximum value. Yeah, actually, it should probably be the minimum value because I've got a minus inside that. Sorry. Yeah. Oh. Never mind. Imagine flipping this up. Upside down. It doesn't really matter how you do this. So the point is that f, the posterior distribution is of the form e to the minus f of theta. So I want to approximate this point here. So if there's a point, if this posterior distribution is well peaked around some particular, the most likely theta star, then maybe I can kind of approximate the function, this posterior, around that point by some analytic expression, and then we'll try to use that analytic approximation to carry out to approximate the integral. So if I want the most likely point, I want then the point which minimizes f, actually, because of this minus sign. It doesn't really matter how you define that, but so I want the point then which minimizes this function, and then we'll try to approximate this by Taylor expansion around that point. So second order expansion. So this says from here we say so f of theta star plus say delta theta, just theta minus theta star. Now, at the optimum point, the gradient is 0. So this first term here will be 0, because the gradient is 0. So we're only going to have this term here. So we're going to have roughly delta theta transpose 1 over 2 Hessian plus higher order terms, which I'm going to neglect. So delta theta is the theta minus theta star, the difference between theta and the optimal point. Okay, so if I want to then compute the integral of this thing over d theta, that's going to be approximately equal to, under this setting, integral of e to the minus f theta star minus 1 over 2 theta minus theta star transposed h theta minus theta star plus terms which I'm going to neglect. Okay, so now you want to carry out this integral. That's easy to do. This is just a constant term. Because theta star is fixed. We assume we know what theta star is. So there's e to the minus f of theta star times the integral over all real space of e to the minus half theta minus theta star transposed h theta minus theta star. Okay, so how do I carry out this integral here? What does it look like?
Gaussian.
It's a Gaussian, right? So basically, this would be a Gaussian with mean theta star and inverse covariance matrix H, right? So what that means is that if I were to say multiply, let's call this thing sigma to the minus 1. So h is equal to sigma to the minus 1. I could then divide by the normalization constant of a Gaussian, which is 2 pi, the determinant of the covariance matrix. And then I'll just multiply that over here. Okay. So this term now here is going to simplify. What would that be equal to? 1, right? That's just 1. Okay, so that's nice. So we get a very simple expression. So this is approximately e minus f of theta star times by 2 pi sigma. Let's say this is known as Laplace's method. I don't know if Laplace really came up with this, actually, but it's called that. So what you need to do to implement Laplace's method is you need an optimization routine which will find for you the optimum theta star. So you need to run some numerical algorithm, plug that into MATLAB, whatever it is, to get that. So that's, we're not going to talk about optimization, fortunately, in this course. When you're at that point, you need then to compute the Hessian matrix and to compute the second derivative of this function f and evaluate it at that point. And that gives you h, the curvature of this function at that point. And then just whack it into this formula. Now, typically, we're not going to use that formula as such. We're going to take the log of it. So we'll write down the log of the integral. So just say the log, therefore, of the probability of the data for this particular model is then going to be approximately equal to the Laplace's method minus f of theta star plus half log det 2 pi h minus 1. And we'll use the fact that the determinant of the inverse is the negative of the determinants. So we can switch that around if we want to as well. Alright, so we can plug in, if we want to, we can plug in now the actual expression. So just going back to my notes. Okay, so what I've written down now is this. So I just jumped straight here. I mean, it's just an exercise, as you saw in multivariate calculus to do that. So now I'm just using the fact that f is actually given by this expression here. So theta star is the max, it's the minimum of f. So in other words, it's the maximum of this likelihood time times by your prior. Okay, so just looking at the geometric picture. Bearing in mind, when will this thing work well? Well, we've got some kind of posterior distribution in theta. If this thing, we're going to basically be taking a point here and then expanding around that point. We're going to approximate that by the Gaussian, essentially. That's what we're doing effectively. But clearly, if this posterior is actually really sharply peaked around a particular point, if it looks kind of Gaussian, then this Laplace's method will work very well. It will be a great approximation, or pretty usually, good enough. If it's not close to Gaussian, it's going to be bad. So it's not a panacea. The interesting thing, though, is that many posterior distributions will typically look kind of Gaussian, and as you get more and more data, this concentration effect happens. If you've got IID data, you get this central limit theorem concentration effect, the posterior stool typically look kind of Gaussian. But without, in the absence of a large amount of data, it's not necessarily the case that it will be Gaussian. Okay. So if you got this kind of thing, a product of data points, then the Laplace's method will just boil down to your function f is given by the log of the prior term plus the log of the likely term, which in that case would be the expression. So one method in the literature, which is just using Laplace's approximation, is called the Bayes information criterion. There are some related ideas, but to be honest, I don't really understand this. I don't really know why people do this. It's always been a mystery to me, and I never found a good explanation for it anyway. Because on the one hand, you could say, well, now I can apply Laplace's method and have a perfectly reasonable approximation, hopefully, to the likelihood of the model generating the data, Pt given there. Okay. What people also do is they say, well, I don't know why, but they say maybe they don't want to, maybe it's too much effort or it's too complicated to calculate this Hessian or something. I don't know, but maybe they don't want to use that. So they say, let's approximate the Hessian by, say, n times by awareness number of data point times by the identity matrix. But the motivation for that is that if you were to go back to here and you compute the Hessian of this, so the second derivative of this function f, you're going to get some constant term here, plus on the IID data, something which is going to scale with the number of data points. So if you've got a large number of data points, which is the limit where we're hoping this approximation will work well, this term is going to kind of be small. It's going to be dominated by this term, because this doesn't scale with the number of data points. So if you say, well, roughly speaking, each of these terms here is, say, it's something which I'll say is n independent. So say if it's order something, let's say it's order 1, then they're going to have roughly n times by an order 1 quantity. And I'll approximate the Hessian of this thing by an order 1, just 1. The identity matrix. So that's the one kind of motivation for this particular approximation for the Hessian. You just replace it by n times by the identity matrix. It's only it's a very, very crude idea. It's just it's true that it will roughly scale like that in terms of the number of data points. But we're losing the real curvature information that's really there. And you can whack that then into your Laplace's approximation, and you get an even worse approximation. So you make this additional approximation in the Hessian, and you get that. And then again, for reasons completely beyond me, people are not even happy with that. I don't know why. And they decide to approximate this even more. And they say, well, let's, for some reason, they decide to use a Gaussian prior. So what if you have a Gaussian prior on theta? Maybe this is from some kind of classical statistics kind of thing where they don't even really know what prior distribution to use. So they say, well, let's just choose some generic prior distribution. Let's choose a Gaussian. Okay, so they choose a Gaussian. So you whack now your Gaussian into here. So then the log of the Gaussian will give you, this is the Gaussian term here with 0 mean. And then this is the term here is the normalizing term of the Gaussian normalizing term will cancel actually this term here. So you're left with this expression here. And even more, they say, okay, I don't even like this this optimal this term here. And then neglect it. And you end up with this expression here. So maybe your optimal theta is roughly 0, and I don't know how they went about that, but this is their final approximation. This is called the Bayes information criterion approximation. So the idea, maybe their idea is, you could say, well, look, this is the log likelihood evaluated at the optimum point. So all that we want to try to understand is how to penalize that. We don't want to overfit. You know, if we use more and more parameters, typically we're going to get a better fit to the data. But that's not what we want. You know, we don't want to use all the parameters. We want to sort of find, you know, to average over the parameters. That's the Bayesian idea. So what you're going to do is, if k increases, is the number of parameters increases, it's going to actually decrement your optimum log likelihood. So you'll increase this term generally by increasing the number of parameters, but you get a trade-off because you're going to start decreasing this term more. So there'll be some kind of trade-off optimally between increasing the complexity of the model and the penalty on the complexity of the model. So increasing the likelihood and trading off the complexity. And this n is the number of data points. So what people will do then is, you know, they say, okay, you know, people use this Bayesian information criteria, and they just run the classical maximum likelihood. Because that's what they do. Is they run, okay, I run maximum likelihood. I calculate the maximum likelihood. K is my number of parameters. Whatever the model is, n is my number of data points. They whack this term on there, and then they compute this score, and then they do that for another model, you know, with a different number of parameters, k prime. And they do it, and then they plot, as you vary k, that k, which is optimal, which has the highest Bayes information criteria. Yeah. So that's the Laplace's method. I don't know why they do that. I mean, you know, this you can, if you want to use the Laplace's method. My strong recommendation to you is to use this expression. I have no idea really why they don't apply that. The only thing that could be, you know, it's not impossible that your Hessian may not be positive definite. That could happen somehow. I don't know. You know, maybe then you can't compute this log determinant and things are, you know, screwed up. But it's very, very unlikely to happen in practice. So anyway, I felt duty bound to tell you about this. It's in the literature. It's a bit hard to justify. Okay, so that's the BIC, and there are other Akaiki information criteria, which is some kind of, you know, another kind of approximation of the answer. There's some people claim this better. I never remember this one because I don't use that. Okay, so we're going to move on to another aspect of Bayesian model selection. Well, before I finish this, I should say, of course, this is the starting point for approximate integration methods. There's a whole, you know, range of other things we could do. This is in the class of perturbation theory, of perturbing the solution around an optimum point. There are all kinds of other perturbation theories we can do. There are numerical methods we can use, like Monte Carlo style methods. There are, you know, adaptive grid methods we can use. There are variational methods coming from convex analysis. There's a whole range of, you know, things that people have been studying for many, many years, from physics to chemistry to statistics to computer science. All different branches of the sciences have been examining this problem. And this is the starting point. Okay, so to finish up model selection, we're going to do one other example, which is, I call outcome analysis, but you should think about this in a fairly general sense. So I'm going to use an example where we've got, say, two classifiers, A and B. And let's say that some outcomes are, things like, say, the classifier A gets this thing correct, so it's a true positive on that particular example. Maybe, or it could be false positive, or true negative, or false negative. Those are, for example, 4 outcomes that this classifier A might have in a particular data point. It could just be right or wrong, it could be 2. Whatever it is, you just there's a set of outcomes, say that this discrete set of states this classifier A can have. And similarly, classifier B is also going to be from the same domain. All right? So it could also be true positive, false positive, true negative, or false negative, for example. And in general, there could be, say, just the outcome of each, either the outcome of A or outcome B is just in this domain 1 to Q. So I'm going to have a set, or an outcome for A and an outcome for B, and then have n of these. So this is going to be just a list of maybe 1, 1, or 1, 2, or whatever. And then I could write this set down as a vector for OA, and then have a vector of outcomes. It's going to be a discrete vector, and so we're going to have an outcome vector for B. And what I'm going to be interested in knowing is, essentially, are these outcomes the same statistically, or are they different statistically? So you could use this, for example, to address questions like, are these two classifiers, are the results from these two classifiers essentially the same, or are they essentially different? Or there are many other kinds of scenarios that you could use for this kind of idea. So this is quite a general problem, and what I mean by that is I'm going to test the hypotheses as to whether or not, if they are different, so what I'm going to mean by that is I'm going to have an independent hypothesis in which these outcomes for A and B are just generated independently by some outcome generating mechanism for A and some other independent outcome mechanism for B. They're not going to be in any way coupled, so they'll be kind of different. They're just generated independently. Or they could be, if they're the same, then both the outcomes are generated by the same mechanism. I want to test which of these two hypotheses for a specific data set is actually more likely. And I use this Bayesian mechanism to do that. So in general, the posterior distribution of a hypothesis is going to be proportional to our likelihood term times by prior on the hypothesis, and this is a normalization term here. In this case, we're just going to have two hypotheses. And I'm going to assume that the likelihood, there's independence of trials. So each outcome we have is just a realization from an independent process. So in other words, if I've got a particular hypothesis, the probability of generating outcomes is just the product over each of the elements of this vector. So now I'm going to make some specific assumptions about these two hypotheses. So the independent hypothesis, the hypothesis that these two outcomes are generated by different independent mechanisms, I'm going to say that the data generating mechanism, the graphical model is just that they're completely independent. There might be some parameters underlying the generating mechanism, say alpha and beta, but they're not coupled in any way, not connected. So this is an independent thing. It's clear that, so what we can have then is that, so OA and OB is going to factorize. So if I just sort of put this over here, I've got the BOA from OB given H independent times prior H independent. So that's BOA OB is the integral of BOA OB over the parameters times by the prior and the parameters. This is our Bayesian thing. We have to integrate over the parameters to get the normal. The parameters in this case are A and B, or alpha, beta. And this is then going to split into two. There's going to be an independent of O and A. So this will break into this point here, times by term here. So we can then just, in other words, compute, obviously, this is the model likelihood for observations A, integrating over A's parameters, and this is the model likelihood for B, integrating over B's parameters. So it's convenient to use a Dirichlet prior because that's conjugate to the categorical distribution, as we've seen before. So I'll choose a prior, an alpha, which is of this form. This is a Dirichlet distribution with parameters u. This is its normalization constant, and I didn't prove this, but this is the expression for the normalization constant. This is ratio of these gamma functions. Okay, so you are free to choose the parameters, the hyperparameters of this prior. So we typically set them fairly innocuous, so say maybe they're all 1 or something like that. So if we do that, that means that for this integral here, the model likelihood is given by the likelihood term itself. So that's just going to be alpha times to the number of times that for A we see it in state Q. So alpha Q is a probability of being in state Q. So the likelihood we're going to get, the contribution in the likelihood is going to be the number of times we see alpha A in state Q. Okay, so there's going to be alpha Q to the power the number of times we see A in state Q, times by product over all of the states. So this is the classic thing what we were doing before. Times by the prior, this is a Dirichlet prior. So that's of course conjugate. So the posterior distribution is of this form. So it's just a u, and this vector, this count vector, is just the number of times. It's got the components that you see, the number of times that particular state observed in the data. And we can do a similar thing for B. So what that means is that this term here, so the posterior distribution H independent is proportional to this prior, this sort of normalization term here, times by these product of these two normalization terms with the Dirichlet. Okay, so that's the independent case, and the dependent case is a similar thing. We're going to say, well, we play the same game. This is the term we're interested in, posterior and H the same, given the observations. So this term here is just basically the likelihood times by the prior. So again, assuming that they're independent, given the sense alpha, you can have OA given alpha and H same, OB, okay, so integrate over the parameters. And again, if I assume the categorical distribution here and here, and a Dirichlet distribution here, it just can calculate this integral very easily. Okay, that now it's a ratio of these two normalization terms, where u plus the number of times you see A in state Q plus the number of times you see B in state Q. That's the Qth component of this vector. Okay, so if I put all this together now, and let's say I assume a priori that I have no preference for either independent or the dependent hypothesis, so they're the same or they're different, then the base vector is just given by this expression here, some known expression just involving the counts of the data, and where u is your hyperparameter. So we're going to set typically this u just for the vector of all ones. Okay, so let's look at an example here. So there are two people here, and they are going to be looking at some images, and they're going to say whether or not they find an image to be happy, sad, or say normal. So states 1, 2, and 3. And so the first person comes along and says, well, for image number 1, I think this person is happy. Person 2 says, I think they're happy too. For image 2, person 1 says, I think they're normal. Person 3, etc. Here, though, person 1 thinks that they're normal, but person 2 interprets this as a sad face. Okay, etc. So this is, kind of classical psychology, maybe experiment or something like that. The psychologist might be interested to know, are these people, are they different? Do people classify these images differently? So we could use this outcome analysis, and we want to know what persons want to classify these images differently, or they classify them the same. We just write that into that expression. This is the count. I'm going to use a hyperparameter all ones. So the outcome for A, which is 1 in this case, is 14, 4, 5 vector. to y14 because there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 ones plus 1 on the hyperparameter. Similarly, there are 3 2s and there are 4 3s for 1. And for 2, the second column, second row, we have 5, 10, 8. So in other words, we have 4, 9, and 7, 1, 2, 3s, and we add 1 for the hyperparameter. And on the denominator, we have z of the hyperparameters, so it's 1 and 1, plus z of the combined counts plus 1 hyperparameter. So the combined counts are, there are, whatever, if you go to, there are 13 plus 4 ones, so there are 17 ones, plus 1 is 18, etc. You run that through and then you get a base factor of 12. So in other words, it's 12 times more likely that these people are classifying these images differently than they are classifying them the same. Okay. So you can, you can of course, if you wish, you could use some kind of classical hypothesis testing from statistics. I don't know why you would want to do that. If you want to do it, you can do that, of course. This is an alternative mechanism. So there are all kinds of things you can do with this. Like I said, you could say if somebody gives you the results of a classification problem and says, this classifier got this data point right, and the other classifier got this data point wrong, and you have a kind of vector of right, wrong, etc. You could say, well, are these two classifiers essentially really the same, performing the same, or are really they performing differently? Is one really better than the other? You could use a similar kind of analysis here. Okay, so I think that's the last slide for this Bayesian model selection. I realized that maybe something I didn't explain very well was, why does this work, this Bayesian model thing? Why does it kind of find the right parameter dimension, or the right model complexity? I don't have a really mathematically simple explanation, at least not at this level, but maybe I can try to give you an intuition as to why this works. So let's say that I give you some data. And your task is to just fit a function through this data. So you could say, well, I could fit a straight line. That's fine, right? It's going to have, that's okay, and maybe it's not fitting the data perfectly. On the other hand, you could say, I could fit the data much more accurately, in some sense. I could say, fit, that goes, supposed to go through the data. Okay, all the training data is exactly modeled by that. But you could say, well, that's a bit too complex to me. I don't really think that's the kind of the right thing. Or you could say, maybe there's something like that. Maybe the kind of complexity that's just right. So how do you find this right complexity? Which is the right model? There are many ways to do it. Cross-validation is one way, which you've learned about in supervised learning, which is a perfectly valid way to go about this problem. The Bayesian way is an alternative, and you've seen how it would work, what we would do, but the question is, why does it work? So one way to think about this a little bit, maybe, is to think about the parameter space. I don't know if I can draw this very well. Okay, so this is going to be our complicated model. Say this purple one here. So it's got a large number of parameters, and this theta is the parameter space. It's not two-dimensional; it's in some kind of k-dimensional parameter space. And we're going to try to look at the posterior distribution. So what parameters are giving us a high likelihood? Well, maybe this is the most optimal parameter. The one that's a single parameter which best fits this data, has the highest likelihood score. But now let's move a little bit away from this optimal parameter. So what does complexity mean? What is a complex model? A complex model is one in which the function, in this case, is going to vary significantly as we vary the parameter. That's what complexity is going to mean. There are many things it can model. If there are many things it can model, that means it must vary a lot as I change the parameter. Right? So what that means is if I change a parameter by a small amount, I could get a completely different looking function, one which would be not fitting this function, this data very well anymore. Right? So that means that the region of space that this likelihood is high is quite small, actually, for a complex model. Because as I move away from this high likelihood region, the likelihood is going to drop, because the parameters will change, which means the function changes, which means it doesn't fit well. Now, on the other hand, you could take another parameter space, and you look at the simpler model, say the orange one. It's the same game. So these are different dimensions in this case. This one's maybe a lower dimensional parameter space. And again, you find the points, which is the maximum likelihood. And you play the same game. You try to look at the volume. Roughly speaking, what is the local volume where the likelihood is still quite high, and that's going to be like this. It's a So now just remind ourselves. Now, what is the probability of the data given the model? What's the integral, the probability of the data given the model in theta, times by the prime theta, d theta. So what this is saying is that the likelihood for the model is essentially the average volume. Let's say for simplicity, this is the likelihood, so you're going to calculate the integral of the prime. Let's say if we set that to be flat, roughly speaking, right? Just for simplicity, let's say we put some kind of, I don't vary this much with the dimension. This would be the one interpretation of that is the fraction of the volume for which you have a high likelihood, roughly speaking. So if this were really zero outside here, this term would be zero. It would be only kind of high in this little local region. So if this were constant, that would be exactly the fraction of this parameter space for which the likelihood is high. That would be the interpretation there. Okay, and similarly, it's the same over here. But for the simpler model, the fraction of the parameter space where the likelihood is high is larger than in the complex model. So even though this point may have a lower value than this point here, the relative volume of this large likelihood region is higher for this simpler model than it is for this complex model. And that's why you get this, if you like, automatic penalty, or automatic complexity adjustment in the Bayesian case. But you only get it because of this integral effect. This is the critical kind of picture, which unfortunately I used to have in my book actually the first draft, but I took it out. So for some, I don't know why. I shouldn't have taken it out. Actually, I should have put it back. And I put in another example, which in the end I think is not very useful. But there are kind of ways to make this picture a little bit more mathematically precise. We can use various ways, like we could say for a reasonable amount of data, the posterior is going to be roughly Gaussian. We can apply the central limit theorems, and we can sort of make a more formal argument, and you can tighten that up. It's okay. But that's I don't know if you get this. It's not maybe super obvious, but that's the basic idea. I think it's time for a break, so let's meet back in 15 minutes.